Almost there. Welcome back, everyone. Well, I think we can get started. Welcome back, folks. So I've a whole bunch of announcements here, but really not too much to talk through. We're currently in section 7.8, but before that, the bigger announcement is that we're coming up to our first exam in the course. The exams are going to be very heavily based on what you did in your homework. So like we mentioned last class, probably the best way to study for the exam is get caught up on these sections. And when you get your feedback returned to you on those sections, make sure you know why a problem might arise, understand the feedback and that kind of stuff. You could also take a look at these sample exam documents that are here. Some of them are admittedly things we've seen before, like the Blake lecture notes. And this is just a roundup of all the homework exercises if you want a one-stop shop of a place to go get random practice. And these are fresh problems, but some of them are way beyond what could really be on a real exam. Their purpose is sometimes those problems are just good extra practice. There's little niche parts of those problems where you're going to be doing stuff that's relative to exam one. And also it's good to just kind of see how that might go. It's good to practice slightly harder questions anyways to prepare for a real exam. You wouldn't want to be practicing just the easiest ones, for example. Other comments I have is, I'm not asking a direct calculator question where you absolutely have to approximate something, but there could be questions like that coming up on exam 2, exam 3. So it's just a good habit to bring your calculator just to be prepared for the exam. If you forgot it, no harm done. I might have a couple spares like this one here. More importantly, don't forget your page of notes is allowed. It's a single page, 8.5 inches by 11 inches, so standard letter size, front and back with anything you'd like on it. I'm not collecting the page of notes, so you'll take it with you when you leave the exam room. And what I would do is just file it away. Once you go to take a look at the final exam, you can look back on those and start condensing down material to one overall page for the final. But my comment here is just a way to try to alleviate stress. I've noticed over the course of teaching this kind of class and other classes, probably the most stressful thing you can do is putting your page of notes together at, say, something like around 5 o'clock on Monday. That's really rough. That's super stressful. The sooner you can start putting down your page of notes, putting them together, the easier it's going to be, more stress-free it's going to be on Monday. I'd say maybe something to do on Friday would be a great idea if you had the time. But the sooner the better, you'll be in great shape. Put this together, study these sections here with your page of notes as well, and you'll be well oriented on where all your information is. You might have a change of heart and decide, oh, I need to add extra information or throw away information that just didn't seem to be needed when you really looked at those problems. So it's not too unusual to have a couple revisions. Only one sheet can be brought. It can't be shared among students. But again, I'm not going to be collecting them at the end. You can add anything you'd like on them. So the exam is over those sections highlighted. There'll be integration by parts, trigonometric integrals, trigonometric substitutions, and partial fraction decomposition. But 7.5 was just a review section, so I'm not directly asking questions out of this section. I'm just asking from 7174, but I mean, if that's a review question, it kind of goes together. Well, any questions at all, folks, about the upcoming exam? Okay. Any questions folks would like to take a look at the moment before we go to section 7.8? Yeah, absolutely. So how does the problem go, or what section or document was that of?
7.3. Yeah, and how to know which, what to use, what substitution to use.
Gotcha. So just picking the substitution is the main thing there. Gotcha. Let's take a look. So let me open up a new document. I would say my best advice for the trigonometric sub, you said 7.2 trigonometric subs? Oh, 7.3. The way I would view that one is definitely grab this table right here. So this table is something I would definitely include on the notes. And with that table in mind, let's look at a few integrals. We're not going to solve them because sometimes these have to be carefully rigged to come out nicely. But let me put down just a few random integrals, and we'll pick the substitution based on them. So maybe it's x5 divided by root. Let's make it 9x squared plus 1. Another one could go 1 over root. Let's make it just a 1 minus x squared. And there's 3 of them, so I need to come up with a third version. Try not to cheat, just look at what I have here. So there's a version where there's something positive, no negative signs. There's a version where it's a constant minus a negative. And there's a version where it's the variable minus the constant. So let's put 25 there. So all 3 of these, there could be different ways to solve them, but they could all fit in the trigonometric substitution table. Let's say we are, well, right here on this one. If you're to pick a substitution for this thing, the major thing to look at is it's all positive. That puts us in this case right here. Anyone see what it should be for the trig sub then? What would you write in for x on that first step? Exactly, 3 tangent, or hang on, it's close. The trick with this one is that a value is a 1 on this one, so it should be really a 1 divided by something. It should really go 1/3 tangent theta. Does that make sense on this one? How do we know 1/3? Well, it's really kind of the next steps. Sure, you have to take dx, which is 1/3 secant squared theta, d theta, but this is the major step. You go 9 times x squared, which you'll square here is 1/3 first, it'll turn into 1/9, tangent squared theta plus 1. So that 9 down right here is going to cancel here. It'll allow that identity to finally get working. And so that's what we would have to do for that substitution. Does that make sense for that one? Awesome. On the next one, let's see here. The major thing I'd be looking at is there's a negative sign and the variable is attached to it. So that takes us to this one. Trig substitution has to be the one relative to sign. So we'll go x equals, and there's nothing fancy here, it's just a 1. So that value takes on a 1 and it's just a sine theta. Next thing you calculate is dx. It'd be cosine theta, d theta. And the root 1 minus x squared is going to turn into 1 minus sine squared theta. And that's where these identities come into play. So it's a pretty brilliant table in the sense that it's really got everything. It's got the reason you need a substitution. It's got the substitution. It's got domain informations, but also tells you how to move through the root, the required identity you're going to need at the same time. So that would turn into root cosine squared theta, giving us a cosine theta. Then we just substitute everything back in, solve the integral. Likewise, this is the last one out, but let's pretend it is just a fresh problem. This one has a negative sign, and this time it's the constant that's associated with the negative. That puts us in this case, and this is when we would use a secant as a substitution. We would go x equals, for that 25, that's this value here, so it just turns into 5 secant theta. The same thing as before, calculate dx and simplify the root. We might as well do it just to fill out the pattern. Dx would be secant theta, tangent theta, d theta. The root would turn into x squared, so that's 25 secant squared theta minus 25. And now we have opportunities for different algebra. We can factor out the square root of 25 from inside here. Get root 25, root secant squared theta minus 1. So the way this is picked is always going to arrange the constant, whether we go 5 or 1/3, to force it so that identity is actually going to work. And there it is. It works right at that step. That turns into square root tangent squared. The domain is positive, so we don't even have to worry about the absolute value. We just get 5 tan theta. So that's the trigonometric substitutions in a nutshell. Again, I would say this is like a vital table. I'd probably almost absolutely put this on the notes for the exam one, notes you can bring. And that's pretty much the only formulas in that whole entire section, really. Any other questions, folks, about that section or other questions? Yeah,
With regards to like tree identities, if there's one that's not the corporate that they're using,
Mm.
on the exam, did you say it was gonna be provided in the question?
yeah, if there's a whole bunch of trig identities like double angle, half angle, reduction formulas, I would say the only trig identities that you really got to be ready on would be these ones. Let me pull some out. There's a couple trig identities that we just use more routinely on the homework in section 7.2. So let's take a look. This is some good stuff right here. All those antiderivatives, I probably definitely would include that table. Some of them are non-standard, but the identities I'm looking for are these ones right here. So we should be ready to go with these two in particular. These are the reduction formulas. There's homework questions based off them where you really can't even move through the homework question until you use those on the right problems. And they come into play whenever you're doing an integral like, say, where did it come into play? I thought I swore I had one. Sine squared. Oh, this one right here. If the power is even on your sine and your cosine, or if it's just this, for example, just sine squared or just cosine squared or cosine power 4, you would need these identities right here, the reduction formulas, to start working through the problem. So I would definitely include those on the notes. But if it's other random things, like for example, sometimes you might notice I put a hint on the homework that there's a double angle identity. There's a bunch of these as well, double angle identities, but a common one is sine 2x equals 2 sine x cosine x. Another common one is cosine 2x equals cosine squared x minus sine squared x. That one's pretty weird. Notice if it was a plus, the whole thing would be 1. But these are not identities I think people are just going to grab out of thin air on a timed exam. They'd be stuff that you'd research on a homework assignment. On an exam, if stuff like this comes up, I would provide that identity. It's more like these kinds of identities where we use them a bunch in the homework and such. Those are the ones we should be ready to go with. So again, kind of the homework is going to decide a lot of these things on what your expectations should be. But other questions, folks, about that? These are good questions so far. Thanks for asking them. Any questions over Zoom?
How many questions are we looking at on the exam?
I forgot how many they are. I wrote it earlier in the week, but I think I'm going for 8 questions total. About, I think 5 or 6 of them are a full question, but there's a few of them where it's kind of like a partial question. What I mean by partial question is something along these lines. Let's see. Sometimes problems are so big that it's just easy to break it up. It's better to break it up. Oh, wrong section. And this is an example when that can happen. So for example, a question like example 2, I might give you just random rational functions and ask you, show the decomposition. Maybe not too much factoring, but it could come up. You might have to factor out an x potentially. But coming up with these forms right here could be a question in its own right. So there's going to be 8 questions total, but a few of them are just faster concept questions. This one was in the homework for section 7.4 of doing those breakdowns. Another breakdown could go like this. Let's do one over here. So again, this is like a partial question, just so that the exam isn't so hugely long. A potential question may be something like this. You're given just a random integral. Let's say it goes about x squared plus 3 sine x dx. The instructions could say something along the lines of determine the values of u, du and dv for which integration by parts can be used to solve this integral. So not the exact wording, but wording pretty close to this right here could be used. And the format might be written this way. U equals, then just a whole bunch of space. dv equals, du equals, v equals. I think I add something along the lines correct. Differential notation is required. And this would be just another example of what I meant by a partial question. So I'm not going to ask for a full top-down integration on all 8 problems. Some of them will just be a concept question. But by the way, while we're looking at this, you can see what the u should be. You could split the integral, but it's easiest to keep it all just like that. So if you didn't split it up, what's a good choice of u on this one? Absolutely, it's the algebraic portion. And by the way, this is a fantastic mnemonic. There's different ones I think we were talking about on the first day of class. But by and large, on the questions that are assigned in the homework, the ones that could be asked on the exams, this would be a really good mnemonic to keep in mind. LIATE. The A there says, pick U if you see an algebraic function, L if you saw a logarithmic, I if it's an inverse function. So going by that, x squared plus 3 should do the job. That took care of x squared plus 3. It leaves behind sine x, so that would go here. When it says correct differential notation is required, we mean there should be a dx here on the dv. Then when we go down a line, the differential of u equals x squared plus 3 is du equals 2x dx. And it's easy to miss that dx. I wasn't super picky on the homework assignment, but for here on the partial concept question, this is our chance to just get it down right. So we would need the dx. Here we need the antiderivative. This one's tricky. Anyone see what it should be? It's got to be cosine, but is it negative or positive? Good call. This one's negative cosine. So that could be a potential question on the real exam 1. Other questions at the moment? Yeah. Half angle for secant tangent. There should be, let's see, if there's one for like, say, we have a reduction for sine and cosine. So if you want a reduction for tangent, you could go tangent squared x equals, you would take this thing, divide by this thing. So now it's 1 minus cosine 2x, 1 plus cosine 2x. After simplifying the 1/2. One for secant, you would have to take the reciprocal of both of this. So reduction formula for secant squared. X would be, flip all this around, and now it's a 2. 1 plus cosine 2x. So it's kind of cheating in a way. I'm just using tangent as sine divided by cosine to form that. And that secant is a reciprocal of cosine. But I think as far as the exam goes, these probably wouldn't come up too often. And the reason being is, although there's a reduction formula for tangent, tangent is squared is easier to integrate here, but it's way harder here to integrate in that format. So trigonometry is really kind of finicky, only because we're viewing it in the lens of use the right identity to make integration easier. We're kind of really shoehorned into certain identities. Other questions about that so far? Or any other questions at the moment? Okay, just to make sure we were giving the online class a chance. Anyone over Zoom have a question about the upcoming exam? Okay, we'll pause the review here. But I do want to mention, oh, I forgot to actually give this a title. Let's call this Exam 1 Questions. I need to pick a place to save it. let's keep that here. And I'll post this as a PDF right over here, so that if you want to come back to what we were discussing, you don't have to watch the whole YouTube video to see it. So our upcoming exam, again, is just over those sections. And what we'll do now is switch gears and go to section 7.8, dealing with improper integrals. Good news there is we're still integrating, so we'll look at integration by parts inside this document. Partial fractions comes up, a U substitution comes up. So even though we're moving forward, this is on exam 2, still plenty of opportunity to practice integration. So let's refresh what we were doing on these notes. I don't often scroll back and start at the very top again, but improper integrals is weird enough. It deserves just a second look through on these notes. So the idea is we want to use the fundamental theorem of calculus, but there is a requirement. If we're using the fundamental theorem of calculus, you must have A, B are finite real numbers. So in other words, that is already a big problem. You cannot use the fundamental theorem of calculus because the interval has infinite length now. Infinity is not a real number, it's just a concept to say there is no upper limit of integration whatsoever. So there's nothing to plug in. You can't calculate f of infinity. Infinity is not in the domain of any function whatsoever. The domain is real numbers. But we can approximate by just making the interval of integration bigger and bigger. We started by integrating from 0 to 1. We got that value. Then we integrated from 0 to 10. Well, we made the computer do it. And here's the graphic. Here's from 0 to 10, 1 over 1 plus x squared. And as that gets larger and larger, the values of these numbers start to settle down onto something. So again, fundamental theorem of calculus works every time here because 10 to the power of 6 is a real number. Down here, t is regarded as a real number as well, but we're just letting t represent t power 2, t power 3, t power 7, and so on. And we put a limit statement in front of it. So because t does in fact represent a real number, you can use the fundamental theorem of calculus right there. So this is what the setup looks like. If you need to do an improper integral type 1, it means the interval is of infinite length. You replace the infinity with the new variable t, and now you take the limit as t goes off to infinity. In fact, let's keep on going with this one, just for the fun of it. Anyone happen to know the antiderivative of 1 over 1 plus x squared? It turns out this one's not a natural log. This one is something else. It's a trig function as by way of hint. So some trig function, if you differentiate it, you get that. You're on the right track. It's tangent inverse. Yeah, it's tangent and derivative is secant squared. But if you go to tangent inverse, the derivative of tangent inverse is in fact 1 over 1 plus x squared. Those derivatives are really weird when you're involving an inverse function. And just to pause right here, by the way, that's also why the last page of the exam includes this kind of stuff. Because it might be hard to spot that a 1 over 1 plus x squared is tangent inverse until you just use it a whole bunch. By the end of the course, that's going to be like second nature. But some of these take a while to really memorize, like that one or that one, for example. So this one just turns into a tangent inverse. It's antiderivative. That means we're taking limit as t goes to infinity, tangent inverse of x, but it's a definite integral, so we evaluate it from 0 to t. We're on our way with this one. I mean, it is weird, but I should have closed that. There we go. But now just an ordinary evaluation gives limit t goes to infinity of tangent inverse of t minus tangent inverse of 0. Tangent inverse of 0 is 0, so that's kind of nice. But how would you solve the limit of t goes to infinity of tangent inverse t? Anyone happen to know that one? That one's digging really deep in Calculus 1 to really know that limit. It's probably one of the trickier limits from Calculus 1. The reason it's so tricky is the way they show you how to do this limit is by observing this information. So pause your thoughts right here and go to this document. So this is review material from Calculus 1, limits at infinity, horizontal asymptotes. And you know what? That's exactly what we're doing. We're taking a limit as t goes to infinity. But if you have a limit as t goes to infinity, and it's a finite number, it just means you have a horizontal asymptote. That's how the limit is solved. It turns out tangent inverse does indeed have a horizontal asymptote. We use that information, we kind of abuse it to get the limit out. Let's put that screenshot in here to show how it works. We'll just put this on the next page. It looks like this is getting longer and longer. There we go. So we're going to use that information. We need to know what the horizontal asymptotes for tangent inverse are. Now this is digging deep in trigonometry. Tangent inverse plots this way. One horizontal asymptote is at negative pi over 2. Another one is at positive pi over 2. And tangent inverse does this. So if we're taking the limit as t goes to infinity of tangent inverse, we're following this path. We get closer and closer to pi over 2. We can get as close as we want by making t sufficiently large. And so here's what happens. As t goes to infinity, this becomes pi over 2. Tangent inverse of 0 from the graph is just 0. So the whole thing is pi over 2, which happens to be what this number is approximating right here. So it looks like, yeah, that's what it was actually really heading towards. So it turns out this curve does have a finite area. It's pretty amazing because this goes to the right forever, and there's always area increasing as you move right. But the rate at which area increases is so slow because the curve goes down rapidly that it actually approaches pi over 2 in the limit. So we say the area under that curve, 1 over 1 plus x squared from 0 to infinity, is pi over 2 after working through the improper integral. Again, it's a pretty weird problem, but any questions so far, folks, with that one? Okay, we didn't do this last class. We pretty much just stopped there. Sorry, say again? It converges. Yeah, thanks for mentioning that. That was another big concept that we were talking about. We'll say converges here. That's actually part of the instructions in the homework, so I'm really glad you mentioned that. Yeah, so here is the big set of definitions. We can have infinity on the upper limit, we can have infinity on the lower limit, or on both the lower and upper limit, which forces us to split the integrals. If the limits exist, we'll say the integral converges or that it's convergent. And if the limit does not exist, we'll say the integral diverges or that it's divergent. So this is strange terminology. It could have been used in Calculus 1. The reason we're hitting it really hard in Calculus 2 is this terminology comes back in chapter 11. And some of these ideas, in fact, come back as well. There'll be something called an integral test, and you just have to do this in chapter 11. So moving on down the notes, here's where we left off. We have an important theorem, but it's a theorem that we will come back to again once we're in chapter 11. Also, the book does a great job of showing the example on that one in your reading. So here, this is where the instruction or problems start. Yeah, go ahead.
But that means then that it converges on a finite point or finite enough, it approaches finite enough.
What do you mean, the finite number that's approaching to? That's a good question. So convergent, well, it's definitely a verb. I'm not too sure why it was specifically chosen, but I think you're on the right track. We're just trying to say either this thing, the area diverges to a positive infinity in area, or it's convergent to, like you're saying, an actual finite number. We're just trying to say, in other words, the limit exists when we convert it to a limit.
I remember it.
Gotcha. Other questions so far?
Previous example, if you get to the sine of x.
Or this example up here?
Yeah, but just kind of similar example, like if we end up getting that sine of x instead of inverse sine of x, I mean that how do we deal with that, or like, it's,
Yeah, let's take a look. So let's suppose you're integrating from something like 0 to infinity, say, sine x dx. This will be an interesting one for sure. So if we were to take this limit, required step is to take limit as t goes to infinity from 0 to t of sine x dx. So that'd be our required first step. And this is actually a really great question. I'm glad you asked this. This is a case where it's going to become divergent, as opposed to up here, it converges to pi over 2. But what causes it to be divergent? We'll see in the next step. This is now limit, excuse me, as t goes to infinity, antiderivative of sine x is a negative cosine x. I'll put the negative up front. Cosine x has to be evaluated from 0 to t. So we use the same upper limit and lower limit from the integral. So now it's negative lim t goes to infinity of cosine t first, looking over here, move that red dot, minus cosine 0. Well, cosine 0 is a 1, so it's now minus 1. Now the limit is for cosine t. This is now a pretty tough calculus 1 problem again. We're really digging deep on everything that happened in calculus 1. That limit doesn't exist. Anyone happen to know the reason why?
it's awfully.
Exactly. For the limit to exist, the curve has to settle on a finite number. In other words, if that limit were to exist, and we put a number L over here, like pi or something random, it means you would have had to have had a horizontal asymptote. But the curve for cosine goes like this. Like you're saying, it's oscillating in this way forever. And that means the limit does not exist, or DNE for our common shorthand in calculus 1. We would say here, divergent. Well, it needs a finite number. Well, range is the way to think of it, yeah, for y values. What would make it convergent? Suppose, for example, that maybe we made a mistake and there's e negative t in front. So totally different problem, but suppose we landed on that step. What would the plot look like? Well, that goes to 0 as t gets larger and larger, so cosine would do this. It would start to look more like that, and it would converge to 0 in that case. But just cosine alone, because it's going up and down, its range is from -1 to +1, never settling. That's what causes the does not exist on this problem. Oh, geez, it does not exist on that problem. Yeah, go ahead.
I forget, what's the horizontal asymptote again?
It's just a number that your curve has to approach closer and closer to. So a horizontal asymptote would be, say, this right here, or that one down below. The tangent inverse, as you go to the right, it never hits a height of pi over 2, but you can get as close as you would like by taking larger and larger values of the variable. Absolutely. I mean, over here, you might arrange something that the algebra gives you some particular antiderivative, but down here, if you have just an ordinary trig function, it doesn't look like you'll ever be convergent. You need like a tangent inverse where it has a horizontal asymptote.
Is there a difference between a horizontal asymptote and a vertical asymptote?
Yeah, vertical asymptotes are what we're going to take a look at for these guys now, improper integral type 2. So a vertical asymptote can come into play if you're looking into this kind of example. Suppose you're integrating from, maybe it's like 3 to 5. I need to think about that, of 1 over, about, let's just make it simple, 1 over x dx. And I need to change my domain. Let's say it's from -1 to 1. We have some major problems on that function because there's a vertical asymptote going through like this, and the curve takes on that shape. A vertical asymptote is a line the curve cannot actually even cross, whereas a horizontal asymptote, it could. So for vertical asymptotes, we're going to handle those with this type of improper integral and other different kinds of discontinuities as well. Other questions at the moment? Yeah,
First section, like, some of these, what they graph like, what the curves are for some of these.
oh, if it was required to know the graph, I would have to produce that graph on the exam. So yeah, for example, it would just be considered rude and just vicious to give this as a problem on exam without the supporting graph, because I'm not assuming you have perfect knowledge of trigonometry, just that you've been exposed to it. I mean, it's been about 30 years since I've taken trig, it feels like. Other questions about that so far? Okay, yeah, so that's a great question. If there's a limit where you need a graph to satisfy it, I would need to include that in exam setting. On the homework, anything like this is on the table because we have the time to do the research, figure out what's going on with tangent inverse, maybe put in a graphic calculator, something like that. Any other questions or comments so far? Okay, these are exactly the questions you would want to ask when you're looking at such a weird topic, improper integrals. So there's two types. Type 1 just means you have an infinite interval. Type 2, we'll see later, means there's a discontinuity, maybe a vertical asymptote, or maybe a different kind of discontinuity as well. So coming down here, here's where we'll take on the infinite types. We have 3 examples to take a look at. And I indicated in the homework, let's grab the homework instructions here. We want to give an overall conclusion of convergence divergence on those exercises. But this is the bigger thing I want to highlight. The limit notation is a part of the problem as well. So I need to indicate exactly what I mean by that right here. Just to be clear, correct limit notation means when we take this integral, we really have to set it up using a limit. So step 1, the required step 1 that we indicate here, I deleted this because I felt like it's just a good idea to do it again, go over it again, is we need to deal with that infinity. If you see positive infinity, you take the limit as t goes off to positive infinity, rewrite the integral, but where you have the infinity, input t. Lower limit is still e, now we have 1 over x, natural log x squared dx. So that's our first step on that one. Any questions, folks, so far with just converting it into a limit? Okay, once we have the limit, we need a good u substitution. But oftentimes you might have noticed if you see a natural log x, that might be just the best choice for a u. So let's go with u equals natural log x. Its differential is du equals 1 over x dx. That means this is the 1 over x dx, just turns into du. Next, let's change our limits of integration. That's always an optional step, but again, it does sometimes simplify work, especially if there's multiple substitutions you have to maneuver through. We'll say as x equals t, that will imply u equals natural logarithm of t. So nothing special there. Next, if x equals e, well, let me keep the color consistent. If x equals e, then that will imply u equals natural log e. We need a value for that one. Anyone recall value for natural logarithm of e? Good call, that one turns out to be a 1. The other value that comes up repeatedly is natural log 1 is 0. And that just looks weird. Let me make that look like natural log. So those are our new limits of integration, and this now turns into limit. T goes to infinity. We're now going from 1 to natural log of t. Here we're going to get a 1 over u squared, or if you prefer, you could write this in as u power negative 2, multiplying du. So that's not a bad integral to get through. This will turn into, let's give a little bit of space before the limit. As t goes to infinity, u power negative 2 and the antiderivative is u power negative 1. So we need an extra negative sign to account for that. We'll integrate that from 1 to natural log t. So finally, upper limit is natural log t. We're going to be plugging it in here, so it's natural log t to the power -1. Or you can now at this stage, because we're done with the antiderivative, call it 1 over natural log t. Then minus, we're plugging 1 into u power -1, but that's just going to turn into a 1 itself. 1 to any power is just 1. So now we need to take this limit, and this one's not so bad. We just need to know something about the natural logarithm function. Would you agree that as t goes to infinity, or let me say it a better way, lim as t goes to infinity of natural log t, it would happen to know that limit right there. What happens in the limit for natural logarithm? This one wouldn't go to 0, it turns out. It wouldn't go e either. Here's a related example to think about. Let's do this one below as a warm-up. What if it was limit as t goes to infinity of square root of t? Anyone see what happened to that limit below? It would go to infinity. The reason being the square root function is just an increasing function, it grows. But so does the natural logarithm. That's an increasing function, it grows without bound. So that goes to infinity. It then means if you take the reciprocal of something that's getting larger and larger and larger, well, this whole thing is going to 0 in the limit. So we now have that this equals negative 0 minus 1. The 0 there is since that limit for natural log went to infinity. But that means the whole answer to this is exactly 1. In the weirdest way ever, if you plot the graph of 1 over natural log x squared, and you're interested in the domain from e to infinity, total area is exactly 1 on that, not a smidgen more or less. So that means we need to give an overall conclusion. This integral converges. Yeah.
So why does it have a limit? Could it just be 0?
Oh, it's all because of what's going on in that denominator. A really great related concept to go along with that one is it's essentially these ideas right here. We're extending on it, but it's the same kind of idea, whether it's something like this, x to a power, or just another growing function. If we look at these really carefully, let's go to Desmos to just get some quick graphics on them. Essentially what's going on is if you have a function that goes y equals 1 over x, it's now x power 1. If you're taking the limit as you're going off to infinity, what you're essentially doing is you're taking something that's growing larger and larger without bound. In other words, the limit as x goes to infinity of ordinary x, well, that would be infinity. The graph of ordinary x is just a function that is rising up and to the right at a 45-degree angle from the positive x-axis. But if that goes to infinity, oh, sorry, there we go, then the reciprocal has to go to 0 in the limit, which is supported by these graphics here. There's a horizontal asymptote at height y equals 0. So the further you go to the right, the closer you get to that 0. You'll never, ever actually hit it, but you can make this as small as you'd like. So that's essentially what's going on with these things. If you bump the power, it's going to 0 even faster, but that's for positive exponents. What happens if it's negative? Now it's shooting up in that direction, but 1 over x power -1, that's just x, giving that ordinary limit. Does that make sense so far with what's going on with those weird things? So the next one is, if you put natural log x down below, then same kind of graph. This one's going to 0 slowly, but it absolutely is. And that's only because natural log itself goes off to infinity. So anything that gets bigger and bigger in your denominator, then the total limit, even if there's a constant of 1,000,000, doesn't matter, it will go to 0. The only thing that would make that foggy now, I'll fix this in a minute, is if it was this. Now I have no clue. That's an indeterminate form, infinity divided by infinity. And thinking back to calculus 1, what are the related concepts there? It's L'Hopital's rule. If you get any one of these indeterminate forms, you cannot resolve the limit like we just did. It requires that kind of stuff. We're previewing it in this section. We'll use it once or twice in the notes. I don't have anything directly like this in the homework, but it's coming up in chapter 11. So it's more of a kind of a preview that this is going to resolve some of the nastier kind of questions. So watch out for something like that. I can't just put down an answer. I actually have to do more calculus to resolve it. But if you have a constant above, this one will always resolve to 0 in the limit, provided the denominator went off to infinity or negative infinity would have worked. Any other questions, folks, with that one there? Okay, well, let me get rid of that annotate. Sorry, that's really hard to read. There we go. So if you were to plot this thing, let's actually plot just while we're having graphing calculator open. If you plot that function, call it y or f of x, it's 1 over x, natural log x, power 2. Looks like some really odd behavior way out here. That's kind of interesting. But do we care about it? Sure, we want the area under the curve, only to that part. We integrate, oh, hang on. No, we don't care about it. Let me try again. We want a domain from e less than x, less than, well, something large. Let's go like 10 power 6. I guess you can't just put e like that. There it is. That's the number e, Euler's number. About 2.71 and some change. Now, if we plot that function, let's try to zoom in a little bit on it. The area under this curve came out to exactly 1. And it seems more plausible because this goes towards the x-axis extremely rapidly. It will never actually hit it, but that's okay. We still have a convergent area. Weird stuff for sure. And what's even weirder is this is actually used a lot in very concrete real world problems because this is all about probability theory as well. Anything to do with the normal distribution used all the time in an applied setting needs an integral like this, as weird as it seems.
It has something to do with how Euler's number was derived. That is derived like that.
Not necessarily. That's a good question, though. You can come up with the definition of an exponential Euler's number through integration, but this one is just more of a one-off, just a weird curiosity. I have a lot more of them on these notes as well. Yeah, go ahead.
So why is it that, 1 over 1 plus x squared example that we did? We put the answer in as, pi over 2. Because
So
approach to the asymptote of pi over 2, but with that one that we just did, we said the area was 1, that the area was 1.
would be the same on this one over here. The area under this function, sorry, say again.
Here on both sides.
Not necessarily. The graph that we did right here was for the antiderivative. But if we're thinking about the area of pi over 2, the graph should have been for that function there. So it really looked like this. And it is symmetric. It does have mirrors across the y-axis. Y equals 1 over 1 plus x squared. But we were integrating from here on out. And this area came out as the pi over 2 on this one. Does that make sense with that question?
If it was pi to pi, then it would be 2 pi over 2.
From pi to pi up here?
Yeah.
I'm not too sure. So you'd have, well, if it was pi and pi, the integral would actually be 0 if you have the same lower and upper limit integration.
Yeah.
But negative pi to positive pi, we would just have to plug it in and see what we would get on that one. It would have been tangent inverse. Can we do tangent inverse? Arctan? That's what they want. Arctan of pi minus arctan negative pi, or that's supposed to be a minus. That would have came out to just some weird esoteric number on that one if we went from negative pi to positive pi. But if you go to infinity on this thing, that's where However, two widely occurs. That's only because this is the antiderivative of the 1 over 1 plus x squared. We got that from the limit. But lots of different ideas interconnect with this kind of stuff. Does that make sense so far with those questions?
Yeah, I was seeing the graph of, tangent universe, not the graph of 1 over 1 plus.
Gotcha, yeah. So whenever we get an answer of convergence, always think it's the area under the integrand, the original thing that we found is converging. Well, other questions before we try another? Okay, let's give this next one a try. So another improper integral, but this one's got a whole lot going on for it. Notice that it's improper because, well, the interval is infinite, but it's doubly infinite. There's no lower limit of integration. There is no upper limit of integration whatsoever. We're saying integrate x times e to the x on the entire real number line this time. Whenever you see that, the trick on this is you want to just pick a number, any real number, to split this up. 0 is oftentimes the logical choice. I can't think of a problem where I wouldn't pick 0. I'd begin by writing this as integrate from negative infinity up to 0 of x e to the x dx, then add to that from 0 go off to infinity x e to the x dx. So that's our first step if you have a doubly infinite integral, no lower or upper limit of integration. We just split it up. And then if you split it up, you can call them I1 for integral 1, referring to this one, plus I2, integral 2, referring to this one, because now the strategy is to divide and conquer. We're going to look at each of them separately. If one of them diverges, the whole thing is divergent. Turns out, well, this one converges, this one diverges, just to spill the beans on it. But just for the sake of practice, let's actually work it out. I'm going to start with this one. If this was a homework question, you want to start with the one you suspect is divergent, because then you do half the work, essentially. But if we didn't know that, and just for the sake of showing how this one goes, we're going to have to calculate I1. So I1 is going to be, first of all, I'll just state it, just to make it definite what we meant when we said I1. It is from negative infinity to 0, x e to the x dx. The required step is we need to write down the limit statement. This time the limit is down, or excuse me, the limit is for t, heading down to negative infinity. So we throw in a new variable like this. But also watch out for the placement of your infinity. If it's a negative infinity, it has to be down below. And that means t has to be down the lower limit of integration. So we're going from t to 0 with x e to the x dx. And at the moment, we just need an antiderivative for that to move through the limit. Anyone see what the technique should be to get that antiderivative? Yeah, absolutely. So this is like the exam 1 review part of the notes. We'll integrate that by setting down a u. Good choice here is not the exponential. Let's make it the algebraic function x. Leaving for dv, e to the x, dx. Differential is du equals dx. And antiderivative of e to the x is as nice as possible, just e to the x. So I'm using the formula that u dv equals uv minus the integral of v du. So that's the mantra of integration by parts. And here's how it comes together. We still have the limit statement. So lim as t goes to infinity. But now we're finding the antiderivative of this thing. I'm going to just put a big bracket. Oh, good call. Thank you for catching that. Good eye. Negative infinity on that one. Then next here, we're going to start putting this together. Take u times v, so it's x times e to the x. Because this is a definite integral, we have to evaluate it from t to 0. Then go minus the integral of v times du. That's going to be e to the x dx. But question first. What do you mean something like negative infinity like that?
They should be able to look right at them.
With Oh, I've never actually seen those kinds of symbols. Yeah, usually for this case, I would just write t to negative infinity without an extra symbol on here. But I have to think about that. Let me write that down. I'm gonna see if I can find that notation there, because that's a new notation for me personally. Negative infinity to a plus. I like that you did mention that because in fact, down here, oh, I have my pen on there, can't scroll. When we go to take a look at these ones, we actually do have to say, as we approach from a side, t goes to b from below, or t goes to a from above. That should have been an arrow. There we go, quick edit on that one. So we will be using those single-sided limits on this case. But if it's a type 1, at least in this book, we usually just leave it as infinity without the extra symbol. Other questions so far? Okay, we're putting it together. We've got, for this integral, we just are taking v times du, so that's e to the x dx. But I have to remember, it's still a definite integral, so integrate that from t to 0. Then it just is kind of a bunch of writing at this point. We'll do the evaluation, an antiderivative, a new evaluation, start simplifying, and take the limit. So now it's limit as t goes to infinity, negative infinity rather, I really like infinity, positive I guess. Plug in 0 first and everything's wiped out. So 0, then minus, plug in t, and we have t times e to the t. Here it's going to be minus e to the x, which is then evaluated from t to 0. And it's simplifying, let's keep on going. Limit, t goes to negative infinity. Okay, that's like the first time I remember to put negative infinity in. Then next it's negative t, e to the t, minus, on this evaluation, e to the 0 is a positive one, minus e to the t. And let's take one more step just to maybe distribute the negative through. Limit, as t goes to negative infinity now, of negative t, e to the t, minus 1, plus e to the t. So we're ready to now simplify this limit. So for doing this limit, well, we need to know what the graph looks like for e to the t. That was not so bad. It has a horizontal asymptote. So here's y equals e to the t. And as you take the limit, as t goes to negative infinity of e to the t, anyone see what that limit should turn into? Absolutely, because there's a horizontal asymptote for the exponential function. This is always 0 due to the direction. If it was positive infinity, we would be getting positive infinity as the answer. So that one goes to 0. That's a constant, it stays negative 1. What about that? There's where the trouble is. And there's the reason why we need L'Hopital's rule for these kinds of notes. So let's pause right here. I'm going to just designate this with a symbol. Let's call it L. Because we need to go on a side journey and find the limit of this thing. The negative sign is not important. If there was a constant -5, it's not going to affect whether that limit exists or not. So I'm going to focus in on this part. Limit as t goes to negative infinity of t times e to the t. First, let's take an analysis on this. What happens to t as t goes to negative infinity? Well, that goes to negative infinity. What happens to e to the t as you go to negative infinity? That goes to 0. Negative infinity times 0, let's pause there. Next thing you want to take a look at is this document, your indeterminate forms. So anything that comes into as 0 over 0, any variety of infinity over infinity, or we have this one, infinity times 0 and the others, these are indeterminate forms. Anything can now happen with these things. This could become 0 in the limit, it could become infinity in the limit, or it could settle on some finite number. Indeterminate means we have no clue. You cannot do this limit by working out any form of arithmetic there. So what we need then is, we need to form a quotient like this. If we can get a 0 over 0, or an infinity over an infinity, L'Hopital's rule can save this limit and give us a real answer without saying it should be zero or it should be infinity. We'll know for sure what it must be. It's all about the rate t goes to negative infinity versus the rate e to the t goes to zero. If one is faster than the other, then we'll have a definite answer on this. So let's write down for the moment. I and d, that's going to be my shorthand for indeterminate. We have to define it at least once on the notes. We take this limit here, and we need to drop something to the denominator. I would say the easiest thing to drop below is e to the t. This will turn into limit. As t goes to negative infinity, t divided by e to the t. And now we need to do a different analysis. What happens to, oh, hang on, we also need to get it right. What should that exponent have been? Not t, but yeah, absolutely. So make that a negative t, and this should work out. So t divided by e to the power of negative t. My mistake is if you switch position from numerator to denominator, you're just switching the sign on the exponent. So now, what's the graph of e negative t? You come up here and you just flip it across the y-axis. Here's e negative t. We're taking this as t goes to negative infinity, so it's following this path, going upwards. The denominator is heading towards positive infinity, in other words. The numerator, well, it's just a variable, so t goes to negative infinity on there. We're also a determinant, but we can use L'Hopital's rule at this stage. Recall L'Hopital's rule, either zero or an infinity over infinity. So we're in business now. We're going to take the derivative of that as an independent function, divide by the derivative of that. So it's no quotient rule. Think of this as a totally different function. So here we go. I always put an h here because everyone seems to agree by your expressions. L'Hopital's rule is weird. If you indicate it, you use it on the notes, it just makes your notes readable, or else it's a weird looking step. So this is limit. T goes to negative infinity. Derivative of t with respect to t is 1. Derivative of e negative t is negative e negative t. The extra negative is through the chain rule. And instead of doing the limit here, I propose we go here. Take that negative sign, put it in front. Limit as t goes to negative infinity. Take the base e exponential, promote it to the numerator. Now it's e to the t. And we definitely know that limit. We're back to that function. So go to negative infinity. The limit on that one is 0. So all that work to say, that goes to 0, the limit. So we're finally ready to satisfy everything on here. If you have to break a problem in the middle like we did, introducing an extra symbol is a good way to just tie the loose ends together. We can now say L equals lim t goes to negative infinity of negative t e to the t minus 1 plus e to the t. And this turns into 0 on the first one, minus 1 plus 0 on the second one. So the whole thing equals negative 1. And what does that say? It means from negative infinity to 0, x e to the x dx, that's the first integral we looked at. We called it I1, converges. But it doesn't answer the question about the total integral up here. We still don't know if that converges or diverges. We'll have to come back after the exam on Wednesday, and we'll look at I2. My claim is it diverges, but we have to show it through the calculus to really explain it. Really long problems, this is one of the things that you get into calculus 2. The problems just get pretty long. The homework problems are not all this long though, so it's a little bit more contained. But this is a section we'll come back to after the exam. Any last questions or comments, folks, so far? Okay, well, while you're studying on the exam 1 over the weekend, don't hesitate to reach out. If you have any questions that you're working on, anything that looks weird on the sample exams or homework questions, those kinds of things, I'll be happy to help out. Also, this is a pivotal week. If you're behind on homework assignments, I don't have a late policy because I really want you to complete those assignments. If you get those assignments in to me over the weekend, anything that you might be behind on, I'm going to make every effort to grade them, return the feedback to you before Monday's exam. For sending them in to me on Monday, I'll still give it a try, but I could run out of time. Monday's my busiest day, or Monday and Wednesday. But have a great night, folks. Try not to work too hard. See you all in Monday's class. You bet. Oh, and for the Zoom people, I forgot to mention, we won't have class on Monday, so it'll be kind of like a day off for everybody, except the in-person class will be in this classroom. The online section will be at the various testing centers.